Hi, in this video we'll learn about stress concentrations in axially loaded members. If we review what we covered before about axially loaded members, very simple formula here is sigma average is equal to P over A. And we were kind of explaining here why we added this text here of average, because we explained that in closer to the load application, the stress distribution is not uniform, and we make an assumption here. So we're trying to see some special cases of axially loaded members. And we see here there are always in machining of members, and when you try to fabricate them, to put them together in connections and all of that, you see that you are changing the cross sections from bigger sections to smaller ones, or you're making holes for connections or whatever things you want to pass through the members. So making notches, so reducing the cross section from D uppercase to D lowercase, or you're making a hole in the middle of the section here. And to design this member, we would think, let's look for the critical section. So whenever there is a reduction in the cross section, this is my critical section. Or if there's a hole, then this is also a reduction of the cross section. And I will take a cut here, take a cut here, figure out, yes, my section is D by whatever thickness I have. And in this case, it's D uppercase minus D lowercase times the thickness. Now, the thing here, curious interest, researchers got interest into what's really happening because of these notches and holes. Because when you do machining for material, you cut a hole and you punch holes through the material, you are actually causing some weak points around these transitions here. So what they did is they do use experiments and use elastophoto approach or methods and to gauge the shear, the stress, really the stress inside this cross section here in the case of notches. And this cross section here in case of the holes. And they found that the stresses in the first case is really extreme in that area where the cross section transitions from a big dimension to the smaller dimension. So if I use my regular average way, this will be the sigma average. But at these 2 points, the actual sigma stress is really different than the average stress. The same kind of observation was here observed in the case of the hole. So where I actually did machining the material at this point here, I created kind of a weak point, or kind of resulted in concentrating the stresses around this point here. So this sigma max is really much more than the sigma average that I assume I can work with. And the idea here is now this is something I can't work with anymore. In this special case, I cannot design that and saying that sigma is equal to sigma average. So what happens is I will consider this concentration of stresses in this case. And what I will do is I will calculate sigma average, but then magnify it with a factor called K, which is the stress concentration factor. So where to get this K factor? There are, from studies, there are graphs and figures that you can use to figure out the K value. So in the case of the hole, you enter from the horizontal axis here by the value of T R over D. And you can see here, TR, basically the diameter of the hole relative to the bigger dimension or the dimension of the member where the hole is at. Once you figure out this value, you go and hit the curve and go horizontally to figure out K. So you can see here, the bigger the hole, so the bigger 2R over D, the less stress concentration you have. But the smaller the hole, so when you are in this area here, the more or the bigger the stress concentration. So that's an interesting observation here to have. In the case of the notches and round transitions, now you have multiple curves. Every curve refers to a different value of D uppercase over D lowercase. If you have intermediate values, you can interpolate. So first you need to figure out what curve I'm dealing with. So it's d uppercase over d lowercase, and then you would go into the horizontal axis, figure out the ratio here of r to d, so r over d, hit the curve, and then figure out the k value. So a very simple way of using the graphs. You will calculate sigma average at the critical section, don't forget that, at the reduced section, and magnify it and increase it by the k factor here. So let's see an example, a quick example of how in numbers how stress concentration changes a little our calculations. So we have here this bar with a hole and a notch both together, transitioning from 40 millimeters to 20, with also a notch here of 10 millimeters. The thickness is 5 millimeters, and there is a load of 8 kilonewton, and we need to find the maximum normal stresses in this bar. We need to find where it is and also the value of it. So to do that, I kind of see two critical sections here. One is at the hole and one is at the notch. So I will consider each one separately and see where is really the maximum stress. So the first section here, I kind of visualize from the slides sigma max, and I call sigma max 1, and sigma max 1 equals sigma average at this section times K1, and sigma average is equal to P divided by the area at this section. The area at this section, I have 40, the total width of the bar, but I have here a hole in it of 20, and times the thickness, so I have 100 millimeter square area. Now, how to get K? I'll use the graph. So this is the graph here, and to use the graph, I need 2R over D. That will be 0.5. Hit the curve, you'll find that K is equal to 2.15. Use the K times the sigma average here, and which is the P over A1, and I end up with the maximum stress in this section, section 1, to be 172 megapascal. Now, section 2 will be a similar process. I will focus on the reduced section of the notch, and that will be the stress sigma max 2 is equal to K2 times sigma average 2, and figuring out A2 here, it's all the same value. One thing I will correct here is that this is millimeter square. So where to get K2 in this case? From the graph, I need to find which curve to use. So D over D, that will be a factor of 2. So I will use the top upper graph, and then R over D, that will be 10 over 20, and that will be 0.5. Now I see here 0.5 is outside of my curve. The graph seems to be going down a little, but I don't know where it will hit 0.5. So to be conservative, I will just take the latest value shown in the graph, and I know it is more than what I would have if I have the complete graph. So I'll just say here that K is equal to 1.75 and use that to calculate the sigma max by multiplying it by sigma average, and end up with sigma max to be 140. So my maximum stress in the whole bar now is equal to the maximum of 140 at 172, so it's 172. So that was a quick example here of how this stress concentration concept is adding that little step to acknowledge that stresses kind of concentrate around the transition of my cross sections or the points where I do machining to the material. So pay attention to that, and it's really critical because materials fail at small points in a member and a structure, and that kind of causes failure over time. So little things, little failures can cause big failures at the end. All right, so thank you for watching. I will see you in other videos. Take care.